Hey, g'day, it's Crusader, and thanks for stopping by today. Now this is episode 8 of building the Crusader model aircraft engine build, and in today's video I want to try to make the connecting rod and maybe make a start on the piston for the engine. I've learned not to make any predictions about what we can cover in 30 minutes in these videos, but that's the goal. And I've got some stock on the bench here which we'll talk about in a moment. And I want to also talk about a side project that I got involved with a couple of weeks ago. And it's an interesting contrast to the work I've been doing on the engine. So we'll look at the bench first, then we're going to have a look at the machine that we'll be using to make the connecting rod. This is the stock we'll be using to make the connecting rod. Now it's 6061 aluminium. It's a leftover from a previous project, and there's enough stock there to get about 4 or 5 different connecting rods out of that. Now at the moment this top surface is just rough sawn, and I thought it would be fun to prepare this on the little shaper that I've got. And you can see I've already made a start there, so we'll go on with that process shortly. And the connecting rod is going to connect the crank pin on the crankshaft to the gudgeon pin or the wrist pin inside the cylinder. Now there is one critical dimension, and that is the distance between the bores at both ends of the connecting rod. Now the diameters of those bores is also important. They really need to be reamed accurately to size or bored to size. And the length of between those two bores there determines where the piston will go to inside the cylinder. So if those dimensions are incorrect, you'll either have too high a compression ratio or too low a compression ratio, or you could smash the piston into the cylinder head. So we do want to get that accurate dimension correct. Everything else about the connecting rod could be just simply marked out using manual marking out methods, and probably just hand cut with a saw and files. But I'm going to do this on my little CNC milling machine because I've got one. And for me that's the most accurate way to make this part, or probably the quickest way. But I want to talk about the CNC milling machine because that's also a lead into this side project that I mentioned. And it's interesting, so we'll go and have a look at that now. So this is my little CNC milling machine. Now this started out as a bog standard Sieg X3 milling machine. I bought it back in 2011, and I bought it with the intention of converting it to CNC. And back at the time there was an Australian company called Promica or Promica. It was really just one person. He was marketing a kit that allowed you to do this conversion. So I bought the kit, and it gave me the stepper motors, it gave me new ball screws and ball nuts, all of the hardware components for the transmission, also a controller, and not the one you can see there. And I made the conversion on the machine and used it successfully, but it was always a bit limited. One of the problems with these Sieg machines is that this column is only 3-sided and it's completely open at the back, and that's because the Z-axis screw is inside the column. Now that limited the amount of heavy cuts that you could do, or the quality of the work you can do, because they suffer from a thing called head nod, which is where the head of the machine, being cantilevered from the column at the back there, wants to move up and down, and that means you get a lot of chatter on heavy cuts. Now I bit the bullet and decided I was going to do a big upgrade on the machine. So what I did was I filled the column with epoxy granite, and I filled the base with epoxy granite, and I moved the Z-axis feed screw to outside the column. Now back at the time when I did it, I was posting some of the build on a forum, and there were all these people who contacted me and said, that's going to be a disaster, it won't work, you've got to have the feed screw in the center of the column. And I think I said at the time, well, you know what, just about every lathe in the world has the feed screw on the outside of the bed, and it works fine. So I just ignored all of the comments, I went ahead and did it anyway, and it's worked fine. So this is the feed screw here. It is a ball screw, it's got double ball nuts. That was the other upgrade I did. I changed all of the ball nuts to doubles, and it's got a protected boot on the feed screw to stop chips getting in there. Now I also ditched the DC motor that came with the Sieg. It burnt out the control board. Cost getting a new control board was outrageous, so I just replaced it with a 3-phase motor, and I fitted a VFD, and that's actually quite a good quality VFD there. Now the other upgrade that I made just recently was to replace the original controller that came with the Promica kit. Now this one here is all new. It's got new stepper drivers in it, a new breakout board. It uses a UC100 motion controller. I've got a new PC, and a new monitor, and it's running Windows 10, and I use CNC as the control software. Now I think it's a great system, it works for me, and although I did use Mach 3 for a long time, I just felt that Mach 3 was getting a bit long in the tooth, and I tried to change over to Mach 4 and I just thought it was too hard. I did try, but in the end I just sort of thought I'll pay for the better quality software, and that's what I use. So this setup here is working really well. I've got a tool cart underneath there with all of the tooling for the little mill and a few other tools, but yeah, it fits in a corner here and it just works. And the other thing I've got is a rotary axis. So you can see it up there sitting on that girt, and that connects to the fourth axis in the controller, and that allows me to do sort of rotary engraving and rotary machining and so on. So yeah, it's a capable setup for me, and yeah, one day I'll buy a Haas, but in the meantime this is going to work. I mentioned this side project now. This all happened about 6 or 8 weeks ago, and I was contacted by a YouTube viewer that lives here in Australia, and he is restoring a 1913 Hudson car. Now he asked me if it was possible to machine some electrical junction boxes for him. Now back in the day, these junction boxes were made of American oak, and they've got to be hollowed out. There's some holes need drilling in them for electrical terminals and so on. And I said, well, I don't own a CNC router, and that's the correct tool for making these parts. But I do have the CNC mill, and I have machined wood on this mill before. Now to do that, I just use a commercially available wood router bit. So this is a 1/2 inch router bit, it's carbide, and it's like the cheapest one I could buy down at the hardware store. And these are designed to run at about 18,000 RPM, but the maximum spindle speed on this machine is 2,000 RPM. But if you keep the feed rate sensible, it does actually work. Now I said, yeah, I'll have a crack, send me some details and we'll see how we get on. Now what he actually sent me were some DXF files. It looked like they'd been made in AutoCAD, and they were full size, and it meant that I was able to extract all of the dimensions that I needed to make a 3D model in SolidWorks. Now I sent Shane a couple of screenshots of the 3D model and also a dimension 2D drawing, and we checked over all the details. There were a few little edits that needed to be done, and then I went ahead and actually made a prototype from a piece of just rubbish wood that I had lying around, and it worked fine. The finish wasn't great, but I sent that one back to Shane and he actually checked it on the car and made sure it fitted. Then after that I set about actually making multiple copies using the American oak blanks that he had sent me. Now I learned a lot about doing tool paths in Fusion 360, and what we ended up having to do was a fairly lengthy adaptive clearing process which hollowed out the inside of the junction box. It also made a pocket in the side and also a large hole down one end which went all the way through the part. Now just that tool path alone took about 50 minutes. Then after that there was 2 different drilling operations. One made a series of holes that went right through the part, and I think they were used to actually hold the junction box onto the car. And the second drilling operation made a series of holes in the bottom of the box, or was probably actually the top, and they were to hold the brass terminal strips and the brass connectors. So here's just a couple of images of the process, and also here's a couple of views of the finished part alongside the original. As you can see, it's a chalk and cheese really. The new ones look fantastic, and I must say the finish on that American oak was excellent. It's a bit like machining Delrin or HDPE. You don't get a lot of splintering, and you get a very, very clean finish on the inside of the part. Now I bundled it all up and I sent it back to Shane, and he got in touch and said, yeah, they're excellent, really happy with it. At the end of the day, you say, well, why would you take on a job like that? Well, it was more to do with learning a bit more about how to do CAM, and especially on complex parts. I learned a lot about Fusion 360 and where all the limitations are with it, especially if you're using the Maker version, and there are a lot. And yeah, it was just an interesting project that I wanted to do. So let's have a look at where it headed next. Now, having completed the work and sent the terminal blocks back to Shane, he contacted me and he said, I've got some tools that you might be interested in and I'll send them to you. And this is what turned up. Now, some of these milling cutters in here, if I had to buy those, that'd be worth like $150 easily. And some of these are absolutely brand new, like that one there. And there are boxes of really good quality small end mills and slot drills, and lots of other stuff as well. There's reamers, piloted reamers. So I certainly wasn't expecting anything like this, but there you go. You do a favour for someone and they'll return it to you. So thanks, Shane. There's enough milling cutters in here to last me out. Not a bad finish for an old machine. I'm going to flip this over now and we're going to reduce the thickness of this to 3/8 of an inch. Okay, 9.57 or 9.58, should have been 9.53. But I could probably run the shear tool over that, but I think I'll leave it. That'll give me a little bit of material to clean up afterwards. There'll be very little left of this surface when we're done. Nearly all of it's machined away, but just on the ends of the bosses there will be one part that's still got this shaper machine finish on it. But yeah, I think I'll leave it like that. I need to cut a 1/2 inch strip off this stock here, and initially I thought I could get it widthways, but it's just a fraction too short across that measurement there, so I can get it lengthways, and I've got enough stock here to get a couple out of this one piece. But I'll go and slice off a bit in the bandsaw, and then we'll head over to the milling machine and we can start setting up for machining that profile. That's just to make the two sides parallel. I wasn't after a really brilliant finish there. This goes in the mill vise now, and we can drill the 2 holes in the ends of the connecting rod. I've got our prepared conrod stock now in the vise on the milling machine, and I've got a big parallel underneath that, but I'll need to move that parallel as we drill and ream the 2 holes that we need in this piece of stock. So we need to drill and ream 3/8 of an inch at this end, and then 1 5/8 inches along in X, we need to drill and ream 1/4 inch, and that will then go onto a fixture with the exact same center distance, and we can then go ahead and machine all the profile of the connecting rod. But the first thing I need to do here is to probe the center of the vice jaws to set my Y position, and then I've got to probe the end of the stock to set X, and then offset to the first drill hole. One of the really good things about this UC CNC software is the number of probing options that you have, and there are actually 2 pages of them. So you can find internal corners, external corners, center of circles. The one that I'll be using is this one here, this pocket, and all you need to do is enter the data in this window down here. So in this case I've just set Y to 16 millimeters. It'll probe up to 16 millimeters either side of where I have the probe set now, and it will automatically zero the Y DRO down here. So UC CNC isn't free. I think it costs, let me check. Yeah, so in Australia, if you buy it from the maker store, it's $97.13. That's a one-off license fee, and after that it's just yours to use. So I find it works really well with the UC100 controller that I've got on this device here, because they come from the same company and they just talk to each other and it just works. Okay, so let's probe in Y. Okay, so that's zeroed out Y at the exact center of the 2 vice jaws there. Now we're going to probe in X. Okay, so that gives me X, and what I need to do now is do a manual data input to find the center of the first drilled hole. Okay, that's my manual data input, and I've zeroed out X, so I can then confidently offset the correct distance for the second hole. So this will be our second manual data input, 41.28 millimeters, inch and 5/8 from this position here. Alright, and doesn't hurt to check that. That looks correct. So I'll go ahead now and I'm going to drill letter C, and then we'll ream 1/4 inch. Check and see if my parallel is clear. That would look rather unprofessional if I drilled into it. Alright, this will come out now, and we can set up our fixture and just drill the exact same distance, 41.28, but I'm going to be tapping that M5, and I've made up some little bushes to go in these reamed holes so we can hold the part down accurately. So this is my fixture plate here. It's just a piece of hot rolled steel, and it's been drilled at exactly the same hole centers as the piece of stock for the connecting rod. These are tapped M4, and I've made these little aluminium bushes that fit through the reamed holes in our piece of stock. So we can screw that down to the fixture. I did have to swap ends with my part. I realized that my NC code had this end here as 0 in X. So that was easy enough to do. And when I get the screw down, what I always do is bring the cutter down, touch the work, zero out the Z in the controller software. Then I come back up 20 millimeters, reset Z, and then do an air cut. just in case there's any nasty surprises. And the thing is, when you're doing this sort of work, every single part you make is a prototype, and there are sometimes missteps that you don't pick up, and you're very lucky if you can actually finish a part first time round without any mistakes. And that's why I prepared enough stock to make about 2 or 3 of these connecting rods. So I'm going to get the screw down really tight. I've already done a check with the NC code, and I let it sort of run through to make sure that it wasn't going to chop through the part or crash into the vise. So I'm fairly confident that that's right. So I'll go ahead now and set 0 correctly, and we'll go ahead and see what happens. But I always keep my finger over the feed override. So I just bring the cutter down onto the top of the workpiece, lock the quill. I'll set 0 at that position there. I know that's not the correct way to do it, but it works for me. So I've reset Z. Alrighty, let's see what happens. Well, did you spot the deliberate mistake? Clearly I didn't set the safe Z height correctly when I did that last operation, which was a climb cut around the inside of that pocket there. So yeah, rookie mistake. Now I've got to try and get those screws out of there and flip this part over. But everything else worked really well. The only thing is that the rapids are disabled when you're using the maker version of Fusion 360. There is a workaround for that, and a viewer told me about it, and I had a look at the website. It's sort of a script that you got to add on, but I just didn't get around to doing it. For these sorts of operations, I don't care that it's slow. I'd rather it be predictable. I don't think it's helpful to have things happening super fast. Something goes wrong, you can stop it. But the finish on that's pretty good. I've got another operation to do. I can flip the part over and we've just got to do an adaptive clearing on the back to take a small amount out of this same surface on the other side. So I'll get set up to do that and get some new screws. Okay, flip this part over now, and just to be sure, I changed the retract height from the top of the stock here to clear the top of these screws, and I also reduced the thickness of those little bushes there as well. So I should be able to clear across the top of those screws without hitting them again. And just to be clear, I've run this NC code 3 times at various different heights above what will be the finished set height, just looking for errors, and I found 2 fairly glaring ones. The first one was that I'd left axial clearance on the top of the stock here, and the other one was that I forgot to change the origin from the center of the bottom part of the connecting rod to the center of the top part. And yeah, that would have ruined my day if I hadn't checked that. So yeah, it's just the way I do things. I'm sure there's people more confident with doing CNC work and maybe have better simulating software. But for me, it's just reassuring to be able to run everything without crashing into the part. So let's go ahead now and see what happens. That last operation was a climb milling pass around the inside of both these bosses, and that just took off 0.2 of a millimeter to leave a better finish. So I'm going to take this out of the fixture now and deburr it all, and we'll try it on the crankshaft. But I'll tell you what, it's a relief to get to this point. There's so much can go wrong. And I did say that doing this with CNC was quicker, or maybe quicker, than doing it manually or on a rotary table, for example. But yeah, you don't take into account the programming time, but I do that in the evening when I can't be down in the workshop. So I get all of that out of the way. I do all the modeling and so on, so I don't really count that as part of the manufacturing time. So the actual time spent cutting metal is probably quicker than doing it manually on the milling machine or on a rotary table. But you know what? It's fun doing CNC when it all goes well. Yeah, I didn't trash my screws too. Okay, I'll give that a clean up. One of the last things you have to do on this connecting rod is to drill an oil hole at both ends. And I've used the same fixture that I used on the CNC mill to hold this part on the Bridgeport. So got a big parallel in behind here held in place with a spring. I was able to push the fixture up against the end of the parallel there to make sure it's vertical. And then I used the touch probe with touch DRO to find the back surface of the fixture. Then you can move forward from there half the width of the connecting rod, and also found the center in Y. So I'm directly over that point there now. I'm going to drill a 2.5mm hole. It's not really 2.5, it's the imperial equivalent, but that's close enough. And we'll do that at both ends. So when I got this end done, I can just flip the fixture. The parallel shouldn't move, and the part is centered on the fixture anyway, so it should be fine. And at the end of the day, it's just to let a bit of oil through onto the rotating surfaces. Alright, so I should be able to just carefully flip that part Alright, same thing at the other end. Okay, let's pull it apart. I'll put it on the bench and have a close look, and then we'll finish up for today. There's a close-up look. I've deburred most of it, and for now I'm going to leave that surface texture on the part there. I like the way that adaptive clearing program leaves that nice pattern on the surface there. Sort of makes you think you're almost a CNC machinist. But later on this is going to get bead blasted. That will soften all of these sharp edges and soften the internal corners and so on. So overall, pretty happy with it. It's not perfect. There is a discrepancy here, so this internal radius here should meet the outer surface there at a tangent. There's actually a hard edge there, so a little bit wrong with the geometry, but overall I think it's turned out pretty good. So I'm going to get this assembled into the crankcase now, and I'll show you one issue that needs to be fixed later on, and also we'll talk about what's happening next time. Now this piston here is not for the Crusader engine. This is a mock-up I made for the Titan 60 engine. It's very similar, the difference being that for the Crusader engine there's a large pocket cut in one side of the piston, and that allows fuel and air mixture to flow through the piston, through the bypass ports and up into the upper cylinder. Now for the Titan engine it was a different shape inside the crankcase, and it didn't need that port. But you can see how the small end of the connecting rod fits into that pocket there, and it will line up with the gudgeon pin. So I'm going to hold over making the piston for the next episode. I know I said I was going to do it today, or I might get to it, but we run out of time. Now the only way you can actually attach the connecting rod to the crankshaft is to take the cylinder out, and then you have to put the crank pin at bottom dead center, and you've got to put the larger pocket on the connecting rod toward the face of the crankshaft, and then you should be able to slide that through and lower it onto the crank pin. Now at that point you can rotate everything and it all looks good, but there's a problem. The connecting rod will clash with the bore coming through the top of the crankcase. Now that's mentioned in the notes, and it says you can either file some clearance there or you can machine a pocket. Now on the drawings they've actually shown where that pocket needs to go, what the angle should be, what the distance should be either side of center, and also from the front of the crankcase back to the center of that pocket. Now if you don't have the most recent version of the drawings, if you get them it'll show you where that pocket needs to go. But I'll do that later when we got the piston done. So for now I think we're sort of tracking along fairly well, and like I say, in the next episode we'll have a go at making a piston, maybe more than one. So join me for that. Now I have actually got some wildlife video to show you today, so please enjoy that, and I'll see you next time. It's Crusader signing out for now. Cheers. I was just walking past this pond here. This is just an ornamental pond. It's normally quite full of water, but at this time of the year when you get the dry season it gets very shallow. And this is a keelback snake. Now keelbacks are non-venomous. They're very benign. Their main food is small frogs, fish, and because the water level is quite low, he's in here fishing, and he'll probably clean out a lot of the small fish that get trapped in the puddles. But he's just completely still because he knows I'm here, and these are one of the few snakes that can tolerate cane toads. The cane toad is the introduced toad. It's noxious and toxic. It can kill a cat or a dog. But these snakes can eat one and digest it. It's not their favourite food, but they can eat it if they've got nothing else. Like I say, he's happy to just clean out all of the small amphibians and the whatever else can find in this shallow water. They're a very pretty snake, got big eyes. They tend to hunt at night a lot. You see the pattern on his scales under the water there, and if you bother these and you corner them, about their only defence is they spread those scales open and the skin under the scales is bright blue, and it's meant to be a warning. Just on the way down the letterbox and nearly ran into this guy. He's only about 3 meters away. You eat that shrub, my wife will be angry. These kangaroos are wild. They tend to be fairly tolerant of us. They see us around a lot. I think they realise that we don't threaten them. But you don't want to get too close.